Welcome to The Explainer. Let's just jump right into it. Today, we're demystifying GPU performance tuning. We are going to take that abstract code you write and turn it into a physical mechanical reality, a machine you can actually control. So, if you've ever felt like your GPU is just this magic black box running your kernels, well, you're in exactly the right place. We're going to look at the specific tuning dials you can turn to command the hardware and squeeze out maximum speed.
Here's our roadmap for today. First, software meets hardware. Then, we'll tweak three main tuning knobs: block size, occupancy, and warp divergence, and we'll wrap it all up with practical rules to get you started.
Section 1. Software meets hardware. To start tuning, we have to map your code to the actual physical GPU. Think of it this way. You write a software hierarchy, right? You've got a grid containing blocks containing threads. But the physical hardware speaks a completely different language. It's a GPU packed with streaming multiprocessors, or SMs, which are split into partitions holding the actual physical execution cores. When you launch a kernel, you are literally dropping your software grid onto the hardware GPU, which then hands out your blocks to its SMs.
So, how do we bridge the gap from a block on an SM down to the actual cores? The secret is the warp. The hardware groups your threads into batches of 32, and that's a warp. This is the fundamental unit of execution. The cores don't just run individual threads on their own schedule. They execute a full warp of 33 threads together in absolute lockstep. Think of it kind of like a 32-person three-legged race. Everyone has to take the exact same step at the exact same time.
Let's trace how this execution flow actually builds. Step 1. The hardware dynamically distributes your blocks across the available SMs, basically mini factories. Step 2. That SM chops your block into those 32-thread warps. Step 3. The SM hands those warps over to the partition's warp schedulers. Now, the scheduler's entire job is to look at its pool of warps and issue instructions to the underlying cores, just trying to keep them constantly busy.
Moving on to Section 2, our first major tuning dial, block size.
This is probably the most common question you'll hit right out of the gate. When you configure a kernel launch, how many threads you actually pack into each block for maximum speed? 64? 256? 1,000? Your choice here indirectly dictates how many warps each SM is going to have to juggle.
Now, you might be thinking, well, bigger is better, let's just max it out. And sure, the absolute limit is typically 1024 threads per block. But maxing this out? Usually a trap. Because if you launch massive blocks of 1024 threads, fewer of those blocks can fit onto an SM at one time. If that single massive block stalls because it's waiting for data from memory, the warp scheduler has nowhere else to look for ready work, and your cores just sit idle. You've severely limited the scheduler's flexibility.
Notice how the physical hardware dictates the ceiling here. Take a look at the max blocks per SM limit. For architectures like the P100, V100, and even a powerhouse like the A100, it is strictly capped at 32 blocks per SM. If you go the opposite route and make your blocks way too tiny, say just 32 threads a block, you're going to hit that 32 block limit way before you ever reach the 2048 thread limit. You basically cap out at around 1,000 threads, literally wasting half the SM's physical capacity. It's a balancing act. You have to thread the needle between blocks that are too big and blocks that are too small.
Which brings us right to Section 3, Tuning Knob, Occupancy.
Occupancy is essentially just a ratio. It measures how full each SM is by comparing the active warps currently on the SM against the theoretical maximum it could hold. Higher occupancy means the hardware's warp scheduler has way more choices. If one warp pauses to grab data from global memory, a high-occupancy SM has dozens of other warps ready to swap in instantly, which completely hides that memory latency.
But hey, it's not just block size acting as the bouncer here. Your code's resource footprint plays a massive role in limiting occupancy. If your threads use a ton of registers, or your blocks request huge chunks of shared memory, the SM physically won't have the space to fit as many blocks. For example, a kernel on an A100 requesting 48 kilobytes of shared memory per block, it can only fit 3 blocks before the SM's 164 kilobyte capacity is totally maxed out. Boom! Your occupancy drops, regardless of what your block size was.
So write this one down. Higher occupancy is not the ultimate goal. Higher performance is. It is so tempting to obsess over getting a perfect 100% occupancy score. But if you shrink your shared memory tiles just to push that occupancy number up, you might actually hurt your caching efficiency and slow down your kernel. You want enough occupancy to keep your cores busy hiding latency, absolutely. But blindly chasing 100% can for sure hurt your performance.
All right, Section 4,
Tuning knob, warp divergence. Remember a few minutes ago when we established that a warp is 32 threads marching in absolute lockstep? Well, what happens to that lockstep execution when an if-else statement pops up and half the threads in the warp need to go one way and half need to go the other? What actually happens when they disagree? This is where things can get a little painful. Because they share a single instruction stream, the hardware literally cannot run the if path and the else path at the same time. It has to serialize the execution. First it runs the if path, completely masking off the threads that wanted the else. Then it runs the else path, turning off the threads that wanted the if. You're leaving execution cores completely idle during each step, wasting precious compute cycles because half your lanes are deactivated.
To avoid this divergence, you've got to be strategic. Try to organize your data so that threads in the same warp naturally take the same logical paths. If you have an if condition based on a data threshold, try sorting or grouping your data beforehand. That way, chunks of 32 threads all evaluate to true or all evaluate to false together. And definitely watch out for early exits and loops. They can instantly cause warps to diverge if some threads finish early while the rest keep on looping.
And finally, Section 5, Practical Rules to Start.
Okay, let's tie it all together into a workflow you can use on your very first kernel. Here is your go-to checklist before you start wildly guessing. 1. Stick to 128 or 256 threads per block. 2. Always ensure your block size is a multiple of 32. 3. Prioritize contiguous memory. 4. Grab a profiler like Nsight Compute to actually check your occupancy. And 5. Keep an eye on your warp execution efficiency to spot divergence.
If you're paralyzed by choice and wondering exactly where to start, 256 is the golden sweet spot. Starting with 256 threads per block gives you exactly 8 warps per block. This is generally just a perfect balance. It's small enough to fit several blocks onto an SM, but large enough that you don't instantly hit that hard 32-block limit we talked about earlier.
And as a quick bonus rule, because we absolutely have to mention memory access, make sure those warps access memory in contiguous chunks. We call this coalescing. If thread 0 accesses index 0 and thread 1 accesses index 1, the hardware groups those requests into a single fast transaction. If your threads access scattered, random addresses, you'll bottleneck the entire system waiting on data, and literally no amount of occupancy is going to save you.
So we've walked the factory floor. You know how the control panel works now, how block size sets the baseline, how occupancy keeps the engines fed, and how minimizing warp divergence ensures those engines run efficiently. The GPU isn't a black box anymore. The only question left is, are you going to let the hardware limit you, or are you ready to get under the hood and drive? Get out there, open your profiler, and start tuning. Thanks for joining me on this explainer.